This joke started from a collaborator of mine who was even more, how do you say, if he was here instead of me giving this talk, probably there would be even more jokes, because I've seen some talks about this, which included Donald Duck during the talk. But so yes, indeed, I will talk about a particular type of multiple scales phenomenon called, which is called in French the canard, and that's why my talk is chasing ducks. And we will chase them, and well, I'll hopefully show you that indeed a transseries, meaning they'll be hiding, but we'll find them. So yeah, hopefully I'll show you that the transseries actually is a very good tool to use in order to find. Sorry. And just to say that, yeah, this is work with my student, Daniel Hazenbichler, Chris Howells, and Chris Lostry, who are both in the audience. So I actually forgot to write, meaning it's non-linearity, right, that it's published, but I forgot to add that. So one of the things is like there'll be a prize at the end of the talk. I'm not sure what. Keeps on changing my words into something else. So I managed to catch a lot of them, but I'm not sure that's what to know. So what are canards? So they appear in single perturbed systems where you have typically a slow scale and a fast scale. You have two variables. You have a slow scale and a fast scale. And basically what happens is that you have a solution that, meaning there's an attractive manifold that at some point, there's a bifurcation phenomena, for example, and it stops being attractive to repel, but the solution is so close to that manifold that it kind of stays and lingers before actually jumping to the new stable manifolds. And it takes some long period of time to do this. And in fact, if you do the reverse system, you can also see this delayed process, and basically this is what is known as the canard. That it stays, then it jumps, and it keeps on going on the unstable manifold, and then it jumps to the stable one. And meaning this has been studied, but one thing that we want to do is like try to understand how the multiple scales. How we can use methods of multiple scales and where they fail and what we can do about them, and how we can use, in this case, transseries in order to actually obtain the results of these multiple scales. So what we're going to say, and we're going to do this, of course, this is in discrete systems. In particular, we're going to use the logistic equation. One of the mistakes, by the way, that they kept on doing is I kept on writing logistic, and it kept on giving me logic. So it might happen at some point. So we wanted to study the time evolution. N is our time, our fast time, of the logistic equation. And it's a nonlinear equation. It has period doubling. So here it's period 1 or no period. Then when the bifurcation parameter here, lambda, gets to a particular value, so here you have an equilibrium solution, lambda less than 3. At this point, there's a period doubling, and then suddenly you have a solution that keeps on swapping between two equilibrium points, which is these two. When you start adding more and more, meaning when you start increasing lambda, at some point you end up from 2 to 4 periods, and then like 4 to 8, and of course by some point you reach chaos. So again, we can see this definitely as meaning a change of dominance in these slow and fast scales that I was mentioning in our logistic problem. But in order to actually see the period doubling, it's not going to be just about determining these scales. It's actually to be able to analyze what that dominance is, to actually retrieve that dominance somehow, either from meaning Early times will be one solution, late times will be another solution. So we want to be able to actually get the solution both at early times and late times. And the dominance will change. So again, this is the same. We're going to study the bifurcation behavior by introducing a small deviation from the period 1. So we're going to try and focus on this period doubling at the moment. And we can study it in two ways. We can assume that this is just a small parameter. So it's very close to the change between period 1 and period 2. Or we can say that we're actually going to have our parameter change slowly. So this is our slow scale, slow time. And in this case, so in the first case, what we're going to be able to see is the passage from no period to the 2-period solution. And in here, in fact, if you go for large enough n, what you find is a first transition, and then a second transition to period 4, and then you still have period 8, and then chaos. Here, as you can see, meaning you could expect that it looks like this, but like as I mentioned, it doesn't look like that. It actually, even though the one period became unstable before this point, before the point that they start splitting, the solution stays in. It's exponentially close to the 1-period solution that it stays for longer before actually jumping into the 2-period solution. The same thing, you know, it stabilized long enough into the 2-period solution, and by the time that it gets to the point where the 2-period solution becomes unstable, it still lingers again before jumping again to the 4-period solution. So how can we study this from the point of view of multiple scales? What does the method of multiple scales give us? We have a slow, which will say the continuous time, because epsilon is continuous, t, and we have our fast discrete time, which is n. And we're going to assume that we have an expansion for small epsilon on all these y's. These y's will have ODEs in t, and you can calculate them. And what will happen? And you obtain a fairly good, accurate result. We're going to compare errors later, so I haven't shown any errors. This is also from their work. And now you see that you don't have the solution leaving your exact result. So, of course, the question is, how do you go beyond period 2? Can you go beyond that? And can you do this systematically, like to go to higher periods? So now I wanted to talk also about what I mentioned earlier, which is now the dynamic map. So instead of now saying that this is constant, I'm allowing my bifurcation parameter to vary very slowly. So again, method of multiple scales and matched asymptotics can be done. Well, they've done it. There's a lot. This would be a whole talk just on this. In fact, if I was going to follow everything. But if you only consider the early time, again, it follows the single period, of course, and then it really correctly predicts the delayed bifurcation. So it predicts when it starts going off, but then the exponentials blow up. So again, you have a change in dominance, and you need now the late time scales in order to actually predict the result correctly. Again, you can do that. You do the same thing for the late time solution. Same thing again. It involves even. I think the late time solution is even more calculationally intensive in the sense that it does take a lot of understanding. So you need to actually look carefully at the system in order to understand the scales that are involved, which was like actually amazing that you've managed to do it like so easily. At least it shows. It doesn't show. I don't think that the paper shows how. If you didn't have an insight about like where things would break down, I wouldn't be able to do it. So, in any case, so if you actually now do the late time solution, you do multiple scales again you do matched asymptotics to the early times, and now what you find is that in fact, at least to the correction, which is I think order epsilon squared, you actually obtain now an approximation, a fairly good approximation towards the two stable manifolds, not just the delayed bifurcation, but actually the asymptotics to those. And again, you could keep on calculating higher epsilon corrections also from these methods. So you'd keep higher epsilon corrections for multiple scales. You need to actually match between early and late times and correct the errors here. So can we obtain the other period doublings again? Can we obtain the higher corrections in epsilon systematic? Actually, this is a systematic way of calculating the epsilon corrections, but are there any other way that I can see this problem? And so now I turn to transseries. So a transseries, because of how it's defined, it's a formal sum on both my small parameter and my exponential scale. It's a natural extension of an asymptotic series. It doesn't need to even be an asymptotic series. In fact, the static problem does not have an asymptotic series. And when a solution depends on distinct multiple scales. And so this is my type of transseries that I'm going to use. And how can I use this series? This is a formal sum. How can I use this series to predict the different dominants that I mentioned? That is what's behind this delayed bifurcation phenomena. The way I can do that is by using different summations. So there's ways of summing these transseries such that I actually sum one of the scales completely, and I can do analytic continuation of that sum and understand the behavior in a different region of that scale. So, and basically when I do that, what I'm doing with the summation, transseries and summation, what I'm doing is providing an asymptotic matching between early and late times. It has, meaning it's been used, transseries, of course, it's been used in many, many applications. In particular, meaning it has been used on matched asymptotics before by Chris Howells in continuous systems. So this is the discrete system, but it's been used in continuous systems. So particular to our interest in terms, I'm talking about summations, but the one that I'm particularly interested in is transasymptotics. What happens in transasymptotics? I have my trans series, and what I do is like I reorder my trans series. Here I have the sum for each exponential, which I'm assuming is small, and then I have a whole series in my small parameter. What I'm going to do is change for each order of my small parameter, I have a whole series of exponentials. And what I'm going to do is sum these exponentials into a function, these omega k's, and actually, if I do have this omega k exactly, and often actually I will be able to get it, this omega k captures the behavior of that exponential scale when it actually is large. So there's no issue, because here, if I have this sum, I need to assume that this exponential is small in order to make sense of this sum. But if I have the the function omega k, I can analytically continue it to large exponential scale, and I obtain my result in that region. So again, static map. I start with my static map. And what I do is I introduce some continuous variables. So now, instead of using n, I'm going to use a continuous variable x, which is epsilon times n. And I'm going to talk about r of x, which when x is epsilon times n for each n, this is just the yn. But rx is a continuous function. And rewriting that equation in terms of this r of x and this x, this is what I obtain. So now I allow a transseries ansatz for my r of x. There's a parameter here, which is my initial conditions. I will tell you how to fix it. There's my exponential scales. I haven't fixed them, but they'll be fixed as well. And then, meaning this, you can see that this is the case. The epsilon parameter starts at m/2. You can allow a general m, and what you find is actually two possible options for m. There's basically two series that show up, one that starts at 1/2 and another one that starts at 0. But you can rewrite them something like this. And actually, for the static map, these are independent of x, so this whole thing depends on epsilon only. So again, that's my static map in continuous variables. This is my transseries ansatz. If I plug this into here and I keep equal powers of sigma naught and epsilon, what I find is a differential equation for a of x. Meaning it's a finite difference equation. It's x plus epsilon minus a of x, which you can expand in x, and you get a differential equation for a of x. And a of x is of this form. So I know what a of x is. I still don't know what sigma naught is, but I will worry about that later. And what I can do is do what I said before. I reorder my transseries. I change the order of the parameter epsilon and the exponentials, and I calculate my omegas of an exponential scale, which I'm calling tau naught. Tau naught is just the exponential scale times some, well, the square root of epsilon also shows up inside there because it comes multiplied by m here. And I also include sigma naught because it comes multiplied by m as well there. Exponentiated. So this is my exponential scale, the tau naught. So the r is given by this. I have a whole infinity of these functions, but actually I have differential equations for them. So I can calculate them exactly. So this is what I just wrote. And for example, for the naught, the 0th one, so I did say that we had two different series, one that started at square root of epsilon. Actually, this one doesn't start epsilon to the naught, it starts at epsilon, sorry. But so I have two different types of series. And I have basically, they're always related. So the even is related to the odd, and then we have a differential equation to the odd. This can be solved exactly. This is what it gets you. It's very easy to see also if you analyze, you can calculate the coefficients for these functions if you expand them in exponentials, for example. And you could see that they have finite radius of convergence. And if you analyze the radius of convergence, you can see that it's in fact 1/3, which is expected from these solutions. But this is the analytic continuation. I mean, it's the exact function. So the interesting thing here is, like I said, in the original transseries, I'm assuming that these exponentials are small. This tau is small. But here now, I can take tau large. And actually, tau large gives me, well, 1/3 for tau large, for example. So I can take now these exponentials to be in any regime I want, these functions in any regime I want. So yeah, and you can extend this. We calculated, I think, up to the second one, but you can keep on going. But one thing I haven't told you is I haven't determined sigma naught, because that's the initial condition. And how to do that is now I have my functions. I plug this. I want to calculate at n equals 0, so R0. And R0, basically, if I take n equals 0, it's x equals 0, and I obtain the sum of these functions evaluated here. And if I do, and I know that my original value was 2/3, so I need to fix this to 2/3. How do I actually solve this? I assume that my sigma naught itself is an expansion in epsilon. Plug it back in, and solve order by order in sigma. Now, of course, depending how many orders I have of these omegas, will give me how many orders I can solve for sigma. So this is our order epsilon squared approximation. This is meaning you can't see the difference. This is the error. This is 10 to the minus 3. You can see that, you know, it's pretty, meaning there's no difference in the one period case. The highest error is as soon as it reaches the 2 period, and then it decreases again. Well, it decreases, it crosses the exact value, but this is just a matter of chance in some way. So it decreases up to some point, and of course, after some point, it will start increasing. Why? Because we expect it to go eventually to the 4 period solution. But still, meaning the error is very small, and this is only including 2 epsilons here. Well, meaning epsilon squared. So it's, yeah, 2 of this and 2 of these. No, 1 of these. So this is what you obtain. So before any comparisons, how could I go further? So I asked, so can I go to higher periods? What I could do is, like, I have this solution that I know corresponds to my 2-period solution, and I can do perturbations now around that regime. But these perturbations are such that what I want is to have x large enough such that this part already stabilized for large x. So I have a large tau expansion for this part. So I'm already in the 2-period solution quite far away, but still haven't reached this one. And basically, you can find the solution, meaning I have these omegas. I can find the solution, in fact, in closed form for how this looks for large tau. So this is an expansion of this part in tau naught minus 1. Because I have the exact forms of the omegas, I can actually calculate the large tau expansion. This alpha is just a sign of cosine of epsilon, something like pi epsilon. So it's kind of it just gives you 1 or minus 1 depending on where you are, but it's well defined as well. And then what I do, well, I also do a transseries answers for the S. I can get my action again, so my exponential weight, and I can see if this correctly gives me the 4-period solution. So this is what, so one thing that I wanted to say is, like, how does the contribution from S of x epsilon looks like? I can analyze what this B of x is. And what it happens is that I have a region where the B of x is, is exponentially small, but not contributing at all. At some point, comes from infinity, the exponential. Remember that it's e to the minus bx, so it comes from plus infinity. And starts contributing already here. But here, this region 2, it's still exponentially small. So you're still in the period 2 solution. The other manifold became unstable, but you're still in the period 2 solution. Suddenly, it becomes of order 1 and starts dominating. And at that point, that's when the 4 period starts being, meaning clearly contributing and being a four-period solution here. In fact, meaning again, you can compare with the exact results. So for the four-period solution, you know that you have four now I can't remember what theta is, but that's a whole other thing. But so we have, meaning four-period has four solutions, right? That keeps on jumping from all the four. And this is the error of the exact, of our solution compared to the exact solution. So this is log 10 of error, which is fairly small. Also, meaning, so they, in the matched asymptotics calculation, they did the two periods. So we can compare with the two period, and you can see that the error for the two period solution is from the trans series is actually generally smaller, up to the same order, epsilon squared. So can we obtain now the 8-period solution? We can do the same thing. We have now the R, we have the S. We assume that we've taken time large enough such that these stabilized. And now I perturbed around that term. And what I get, again, is another exponential, which now is not there at all up to this point that goes to plus infinity, comes from plus infinity, contributes, but it's exponentially small. And at this value, which is the value that one expects the 8-period solution to start appearing, it becomes of order 1, and you get the 8-period solution. By the way, I haven't mentioned, but this imaginary part jumping like this is quite important, because that imaginary part is the one that also allows us to see the jump between the different periods. So what happens then in the dynamic map? Sorry, oh, and I forgot that this was the static, so I didn't have delayed bifurcations. I just had the different periods appearing for different lambdas. Now in the delayed bifurcation, you can actually do the same thing, but now the parameter changes with n. If I do the continuous variables, now here instead of epsilon, I have an x. So the equation actually changes. But the idea is the same. I introduce trans-series ansatz. I have my initial conditions. Now these coefficients depend on x, and they're asymptotic. I solve for equal powers. I get my a of x. It's quite different. Now the log, instead of being 1 plus epsilon, is 1 plus x. I can reorder the series, calculate my omegas. And as it happens, at least for k equals 0, you can rewrite the omega 0 of tau 0 for the dynamic case in terms of the general solution for the static case. So depending on how many terms I calculated in the static case, I can reuse them and calculate corrections for the omega 0. And that kind of comes for free because we already did the static case. So if I analyze what we had for the omega 0, this is the solution we have for a comparison with the exact results. This is the error. And so this is the non-periodic case. Then again, it jumps. Anyways, I've put the wrong figure in the previous one. Sorry. This is what happens when you didn't sleep. So again, this is the idea that I said before. I should have, the previous figure was wrong because I thought I was already talking about the dynamic case, and I put the wrong figure in the wrong slide. I'm sorry. In any case, because this type of behavior actually doesn't happen exactly in the first one. So I've already spoken about this. So the highest error is actually when it happens at the delayed bifurcation, and you have here the non-periodic, you have here the transition, and you have here the two-period solution. So this is now comparisons. So in the non-period solution, comparison with the asymptotic matching, you can see that actually the trans series behaves worse. The trans series is quite good at including exponential factors, but matched asymptotics is quite good at giving an algebraic correction in epsilon, which is what happens in the no-period solution or one-period solution. As soon as you go to a transition and to the two-period solution, they swap, because then the scale, the exponential scale, becomes quite important. And this is what you can see from these 2 points here. So just as a summary, and again, I'm very sorry that I kind of did the wrong slide in the, I don't know what happened there. So yeah, transseries and transasymptotics. It already includes multiple scales, because when you write the transseries, and matched asymptotics when you do some summation. It effectively provides up to 8 periods solution in the static logistic map, and allows to predict completely the 2-period solution in the dynamic map, but we also managed to actually predict the 4-period exponential scale as well. But it's, meaning, of course, it's much more difficult in the delayed bifurcation case. And beyond discrete multiple scales, of course, the same methods can be used in the continuum matched asymptotics, and also for other cases like nonlinear ODEs, such as prediction of poles. And I'm going to say that Chris Lustry will actually speak briefly about that. And thank you.
Can the transseries tell you anything about chaos?
Meaning,
Meaning,
from this way,
just,
it can keep on telling you how
you can construct more and more periods.
How to construct higher ones. But there's a big difference between that and actually understanding the path to chaos. So,
I mean, it gets the. Sorry, go on.
So one of the problems you'll run into is whenever you have a period doubling bifurcation. One of the problems you'll run into is the gap between appearances of doubling decreases geometrically with Feigenbaum's constant, which means eventually that gap will be smaller than the small scale, and there's no hope of going past that at least.
Okay, it was a very vague question. It's just, I was wondering, in this way that you do the summation, are there other summation possibilities or other summation methods, instead of summing all the exponentials first, or something that would reveal other kinds of solutions? But it was a very vague question.
Meaning, it depends on where you want to analyze your solution, right? So here, the main thing is that those exponentials go from very small to large. So if you don't sum them in some way, you're never going to see them from a perturbative analysis directly. You need to change scales, basically, in order to actually see.
Asymptotics is summing in one direction, and the summation that you're doing is summing in the other direction, right?
So yeah, you could do that, but in that sense, you're in a regime where your exponentials are small. So, and that would be more like the algebraic small parameter sum.
In your transasymptotic method, once you have resummed these exponentials, you're still left with a series in powers of epsilon. Does that series have the same type of large order behavior as the starting series, or and do you control it? Can you resum, etc.?
So for the static case, that's not an issue because it's convergent, the series. So in general, yes. So in general, yes, it retains the same behavior. Meaning you can do summations on it, but it's a bit trickier just because when you typically, especially if you imagine that you're trying to do optimal truncation of an asymptotic series, you stop at the coefficients themselves depend on the variable that you're trying to define the optimal truncation. So it's a bit of a strange optimal truncation. And I don't even know if we can call it exactly optimal truncation. But in any case, if your original series is asymptotic, that will be factorially divergent and asymptotic.
I may have misunderstood you, but I got the impression that you didn't evaluate all these terms and then resum them. You managed to write down equations for the resum thing. So essentially what your exponentials did was told you what variable to use. It was almost like just a change of variable, right?
Yes, but I guess that's what happens, because when you write the transseries for it, you get, meaning when you start solving for the coefficients, the first thing you get is the exponential scale fixed. And once you have that exponential scale, it's exactly what you're saying.
Then it's essentially a change of variable and almost back to regular asymptotics again.
Yes and no, because it's a change of variables, but now you have two variables again. One is your exponential scale, and one is your small epsilon, right? And the one still depends on the other. So hidden in the exponential scale, there's still dependence on epsilon. But I guess it's a rescaling. In that sense, you're right. It's just a rescaling and redefining your equations for this new rescaling. But the new rescaling includes all exponentials.
Yeah. Anybody else? Okay, I'd like to ask Phil's question again in slightly different language. Is this telling you that there's a new scale that comes eventually? What you say, the onset of chaos? And is there some way of predicting that new extra scale? That at some level of bifurcation, things change again?
So, meaning, I don't think the thing is that the scales start appearing closer and closer together, right?
Okay, but...
And at some point, meaning I don't know if you can really separate all the scale, meaning you're doing perturbations on top of something that has, so in this method, you're assuming that your solution has gotten exponentially close to the original, to whatever period you're in, and you're perturbing it on top. At the point that the difference between the exponential scales is so small, I am not sure you're not going to get into trouble with that, and just the procedure will break.
Right, no, that's clear, but will it tell you what to do to fix that? Maybe there's some new scale that you need to introduce.
So maybe it will, meaning we haven't done that. So you're saying that somehow keeping on doing this procedure would tell you what the new thing to, like...
I'm asking the question, yeah.
So I don't, meaning I don't know the answer to, of course, but...
I mean, is it a particular feature of this map that happens? No, okay.
Meaning in terms of this, I think it's that you have this new scaling showing up. I don't think so.
Okay. Any other questions? No? Okay, let's thank Ines again. Thank you. Okay, we have another break now, and we'll start again at 4 o'clock. Unfortunately, the speaker for 4 o'clock, his flight got cancelled last night in Geneva, so he's going to give the talk virtually. So we'll set that up, but that'll start here at 4. Okay, thanks. And a reminder to this sheet here, actually I think I'll put it on the table outside there to fill in information if you anticipate having some problem due to train strikes or whatever. If you can put down what time you need to arrive at either your train station or airport. Thanks.